we're going to look at Kepler's 3 laws. The first law is a statement of how the planets move. The planets move in an elliptical orbit. The sun is at one focus of the ellipse. So the path any planet takes around the sun is in the shape of an ellipse, and an ellipse has 2 foci. The sun is at 1 foci. This works for any system. So if an object is going around the Earth, the object will take a elliptical pattern, and there'll be 2 foci for that ellipse, and the Earth would be at one of those. So the first law is just basically saying the planets don't go around in a circle, which is what everybody believed at the time. Let's look at the second law. Kepler's second law is an observation. He noticed that a straight line joining the sun and a planet sweeps out equal areas in equal intervals of time. What that means is, if it took 1 month for the Earth to go from here to here in its orbit, it would take 1 month for the Earth to go from here to here in its orbit. And he noticed that this area was exactly the same as this area, which meant, since this line was so much longer, that this didn't have to be quite as long for the areas to be equal. So as a result, the planet must be going slowly here, but quite a bit faster there. So the law is about the areas being equal for an equal period of time. But the understanding is that what it means is that the planet is speeding up and slowing down in its orbit in order for this to happen. And he didn't understand why this was. But the important thing was, it showed that there is some kind of relationship here of the planet's orbit around the sun. And so there must be some mathematical relationship that someone will figure out, and that someone was Newton. Kepler's third law is a formula. The formula is K is r cubed over t squared. What the variables are, K stands for Kepler's constant. It's in meters cubed per second squared. R is the mean radius of orbit. If we have the sun here and the Earth going around the sun, or any planet going around the sun, we already said it goes in an ellipse, so the radius is going to change. So we use the mean radius to do this calculation, and it's in meters. T is the period of orbit. That's the time it takes the planet to go around the sun once, and that's got to be given in seconds. So for a system like the sun, with the sun at the center, we have a constant, 3.35 times 10 to the 18 meters cubed per second squared. So any planet follows this relationship. What it means is there's a relationship between how far the planet is from the sun and how long it's going to take to go around the sun. This formula is good for any system. If we use the Earth at the center, the object in the center controls the system. Just like the sun, you could say, controls our solar system, so we have one constant for it. If I put the Earth here, and I have the moon going around the Earth, or any satellite, it must also follow this law. But the constant will be different. Because the Earth is at the center, it'll be a constant based on that system, and it would be a different number. Just like if I had the planet Jupiter, objects orbiting the planet Jupiter, if we put a satellite or there's a moon around Jupiter, then it would follow this law, but it would be a different